Hi guys, welcome to lesson 3 of our video lessons. Today we're going to be having a look at electric fields as we have been doing, and we're also more specifically going to be looking at the strength of electric fields. Now, how do we know if there is actually an electric field present? Now basically we test for the presence of an electric field by placing a charge there, and then if this charged body actually experiences a force, then there's said to be an electric field there. Now, basically, the stronger that this field is, then the more force is going to be placed on this little charge that we've put there. Now, we can use strength, the strength of this force, to actually measure the strength of the electric field. So if you're in a field and you experience a force, then there's said to be an electric field there. So we define this as the electric field strength vector. So that's basically E represents the strength of the field. So the electric field strength vector at any point in an electric field is defined as the force that's exerted by that charge on a second positive test charge that we place in the field. So basically we test for the presence by imagining some tiny little positive test charge. If we put that near something, if it experiences a force, then there's a field there, and how much force is it experiencing? Well, that tells us how strong the field is. So we can have this equation here. It's saying that E, or the field strength, is going to be whatever the force experienced by that charge is over the size of our initial charge. So the units for this are going to be in newtons per coulomb minus 1. Now, the direction of this field, however, is going to be dependent on our test charge. If we put our little positive test charge there and the direction of the electric force on the charge is parallel, if it's positive, to our field lines, and we'll have a look at an example of that in a moment. But if our test charge is negative, it's going to be anti-parallel or opposite to the field lines around our initial charge. So this is the diagram that we looked at of field strength, and how we measure that is how dense the lines are and the direction based on what sort of charge we're looking at. So if we have a positive charge in the middle here, and we know it's positive because the field lines coming out are moving away. If they were going the other way, it would be negative. But we say to find the electric field strength at any point, for example, this over here at point A, in the field of a single positive charge at the distance r away from it, like in our diagram, we place our small positive test charge, and we're going to call that Q+, and we're going to pop it here and see what kind of force that it experiences. So we've got our imaginary little test charge over here, and we can find the force by using our formula here, and it's basically our Coulomb's law equation. So the force that something experiences is 1 over 4 pi epsilon naught. Q1, Q2 are our two charges. Q is our big charge in the middle, and Q, the little one, is our test charge that we've put in there to determine whether or not there's a field. And our R squared is just simply how far away from our charge we're wanting to know the field strength. We can substitute in our formula we talked about before, so for field strength. So E, or electric field strength, is equal to the force divided by the size of our charge. We can pop that in, substitute in our initial one up here, all right, for F, cancel out Q's, and we end up with this here is our formula for electric field strength. So 1 over 4 pi epsilon naught, or when we substitute in for vacuum or for air, it's 9 times 10 to the 9. And here we have just the single Q, which is our initial charge in the middle, over the radius that we're trying to find, so how far away we're testing for the field strength. So an example, if we are trying to calculate the field strength, or E, at a point that's called X, and it's 3 centimeters away from a charge, and our initial big charge in the middle is going to be a positive 6 microcoulombs in a vacuum, remember, that we're given the medium, so that's good. So our formula E is 4 pi epsilon naught Q over R squared. Substitute in all our numbers we know, 6 times 10 to the negative 6, because it's a microcoulombs, is to the negative 6. At the bottom there we have 3 centimeters. We know that 3 centimeters is not meters, so we have to get our SI unit to meters, which is times 10 to the negative 2. And then it's going to be squared. Don't worry about a little negative up there. we'll figure that one out. I'm not sure why that's showing up there. But if we get that, we have our field strength at 6 times 10 to the 7 newtons per coulomb minus 1 away from the charge. And we know that it's away because our initial charge is positive, which means our field lines would be coming away from it. And remember, if it's a positive test charge, which we imagine it is, okay, we're always imagining a positive test charge unless we're told otherwise, it's going to move in the direction of the field lines. If our field lines are going away, then it's going to be going away from the charge. Okay, a second example. If a charge of, so instead of our positive test charge, we're given a test charge to test there. If we place that at point X, what force is it going to experience? We have our initial calculation here. We know if we're looking for a force, we can just pop it into our simplified version, rearrange to get F. And we know that it's going to be the field strength, which we calculated because we haven't actually changed any distance away. And the same distance around the charge is going to have the same force, the same amount of field strength. So we keep that, and then we put in the size of the charge that it's going to be using. So that force is given to us by 6 times 10 to the 7, which was our E value from the previous, the previous slide. And then we're timesing that by the actual size of our charge. All right, 10 times 10 to the negative 12. So that's going to give us 6 times 10 to the negative 5 newtons of force, and it's going to be away from the 6 microcoulomb charge, again, because this is positive. It's going to be in the same direction as the field around this one. So remember, the lines came out, so it's going to be moving away from it. If this was a negative 10, then it'd be going towards, because a negative charge goes opposite or anti-parallel to the field lines around our initial charge. Okay, so like when we were doing our last lot of example with force, if we want to calculate the electric field strength due to 2 or more charges, it gets a little bit more complicated, but we must first calculate the individual field strengths, and again we have to add them vectorially. Poor spelling. Okay, so if the field at any point is the result of a number of fields, then our total, or ET, E total, is found by vectorially adding the individual field vectors. So the force that one experiences due to the other one, and then the other one, and then we add them to figure out what the total E is, and remembering that this is how we calculate E. So the steps. When we calculate the electric field strength due to 2 charges, the first thing is we calculate the magnitude of E due to each one of these charges. So we use this formula here. Secondly, we determine the direction of the field strength. So remembering that if it's a positive charge we're putting near it, it's going to be parallel to its field lines. If it's negative charge that we're putting near it, it's going to be opposite its field lines. So it's always helpful to draw a little diagram and determine which direction the field lines around our initial charge are going, just to help with this step here. Next, we have to add or subtract the 2 magnitudes depending on whether the fields are in the same or in the opposite directions. So if they're both going in the same way, i.e. they're both moving away from our initial charge, then we would add them. If they're going in opposite directions, one's going away and the second one's going towards, then we would minus them. All right, so that's going to be our example. That's the end of our theory part, and I'll actually show you an example of how that works. Okay, so we've got a bit of an example here about that more complicated situation that we just talked about. So it's called one-dimensional superposition, which is actually a fancy way of saying 2 or more charges that we're trying to figure out the electric field strength. So our question here is we have 2 charges, one of positive 2 microcoulombs and one of negative 3 microcoulombs, are separated by a distance of 20 centimeters in a vacuum. Calculate the resultant electric field strength at X, which is in the middle, of the 2 charges as shown in our diagram here. So that's our first question. So the best thing to do is to write down all the information that we have. So first of all, we know that Q1 is equal to, so we can write Q1 is equal to positive 2 microcoulombs, and we know that that is equal to 2 times 10 to the negative 6 coulombs, and Q2 is equal to minus 3 microcoulombs, which is equal to 3 times 10 to the negative 6 coulombs. And we also know how to calculate field strength. Well, now we do. It's E is equal to 1 over 4 pi epsilon naught, and Q on the top, and R squared on the bottom. So we have our formula, which is always good. Now we can calculate the first part, which is the field strength of field strength E1 due to the charge Q1. So that just means if we're standing at point X, we're getting acted on by 2 electric fields. We're going to feel some of the field that's from Q1, and we're also going to feel some of the field that's coming from Q2. So we're going to experience some different forces from each of these charges. So we want to, so if we have a look here, we're standing here, we're getting some of this one and some of this one, and how much of that sum is going to be dependent on how big those charges are, and we need to add them up individually, which is what we're doing now. So the first thing we have to do is see how much we're going to get from Q1. So we work out, let's figure out what the E1 is. We know that 1 over 4 pi epsilon naught is 9 times 10 to the 9. We also know that Q1 is up here, which is 2 times 10 to the negative 6. And then we know what R is because we're told already that it's 20 centimeters. But we're only here in the middle, which is 10 centimeters, which is going to be, moving things. If we put that down the bottom, we can say it's 10 centimeters or 0.1 meters. So we can just say 10 times 10 minus 1. Or you could just write 0.1, and all of that is squared. So if we work that out, if we get a magnitude of 1.8 times 10 to the 6, and remember our unit is going to be newtons per coulomb minus 1. Now if we are standing in the middle here at X, and we have a force coming, electric field coming out from this guy here, it's going to be pushing us this way, isn't it? So we're standing on point X. What's happening to us? We're getting pushed from just this one, ignoring everything else. The field's coming out of there, so it's going to push us towards Q2. So we say that we're going, let's just say, to the right. All right, so we're imagining that we're a positive test charge, okay? If we are positive, this guy here was positive, so our field lines are coming away from it. We're going in the same direction of the field lines, which means we're going away, and if we're going straight, it's going to go to the right. So we've got that one. Now we have to figure out the electric field strength E2. If we do that, move up a little bit. So there's a couple of ways to do it. E2, we can do it by proportionality, which is the way the examiners like to do it. So let's do it by first. So by okay, which means because we've got one that's 2 microcoulombs and one that's 3 microcoulombs, we can say that E2 due to charge Q2 is going to be 1.5 times what it was from E1. And that's because 3 is 1.5 times 2. So remember, when we have the only thing changing is the size of the charge, then the electric field is going to be changing by that amount. Because we haven't changed any of these factors, it's going to be exactly the same. So E is directly proportional to Q. So if Q is 1.5 times bigger, then essentially E is going to be 1.5 times bigger. So you can work it out like that. And that would also be if we did that, so E2 would be equal to 2.7 times 10 to the 6 newtons per Coulomb. And again, if we think about it, we have a look at our diagram up here. If this charge is negative, all right, which it is, it's negative 3 microcoulombs. So we're standing here. Negative field lines will go in towards the charge. And remember, if our test charge is positive, it's going to be in the direction of the field lines, which means it's going to be going this way in towards the charge, which is essentially also to the right. Now, the alternative to working this out by proportionality and saying that it's 1.5 times bigger is just to plug in all your values again, which should also be completely acceptable. It's entirely up to you if you want to go through and do that. It's a good idea to try and use proportionality where you can, because it does mean that your workload is a bit smaller and you can get through test questions a bit quicker. But by all means, do it the other way if you can't think of proportionality or you don't, you're not quite able to figure it out. Okay. So now we've got E2, we can work out our E total due to those two charges at that point. So we just go, back. We have to do E1. Because they're both going to the right, we add them. These are vectors, yeah. So E2. So we can work it out. E total is going to equal, if we add those two together, we get 4.5 times 10 to the 6 newtons per Coulomb minus 1. And because we're going from the right, adding on to the right, it's again going to the right. Excellent. The other example, or the other part of this question, if we go back to the top, is what would the electric field at X in the middle here be if instead of Q2 being negative 3 microcoulombs, if it was changed to positive 3 microcoulombs, what would happen? Well, essentially there's only going to be one difference, is because the magnitudes and everything is changing, the only thing that's going to change is going to be the direction. So if this was positive, all right, all that would happen is our field lines, if we drew them on, would be coming, we can actually draw them on. So if it's positive, we can draw them on. Now they're going to be going away. And if we're standing at point X, instead of, because we imagine this to be positive, we're going to move in the direction of the field lines, which means we'd be going to the left in this circumstance rather than to the right like we were before, which would change E2, instead of being to the right, it would now be, so question 2, E2 would, the left. So now they're in opposite directions. So if we were working out E total, we would now have to go E2 minus E1, all right? And the reason we do E2 minus E1 and not E1 minus E2 is because E2 is the larger and we're trying to find the difference. And the reason E2 is larger is because it was a magnitude of 3 microcoulombs and E1 was only 2 microcoulombs. So we're trying to find the difference. If we did that, we would get a new magnitude because we're going in the opposite direction, and that would be 9 times 10 to the 5 newtons per Coulomb minus 1. And we'd be going, because we said before E2 is the bigger, we would feel that at point X more than the E1, or the pull from E1 would be going to the left. All right, so just imagine yourself sitting in that little point X, and which push or pull you would experience from each of those two charges. So hopefully that makes sense. Make sure that you write down any questions that you have and we can clarify this in class, but hopefully that has helped to clarify any of the process behind superposition.